Hi, Jack Simons again. I'm going to now try to walk you through the first chapter in the second edition of Theoretical Chemistry. Let me just remind you of all these web links here, in particular the one where you can download the free chapters. So in Chapter 1, we deal with the basics of quantum mechanics, and this is fairly typical of the undergraduate quantum part of physical chemistry class. We want to know, why is quantum mechanics necessary for describing molecular properties? This involves knowing about the Schrödinger equation, which has in it operators, wave functions, the equation itself. It's a partial differential equation. Then there's some applications of this Schrödinger equation to particle motion in one dimension, so-called particle in a box. And one of the important things in this whole discussion at the early stages is to look at the spatial probability densities. That is, what's the probability of finding this particle at various points in space predicted by quantum mechanics, and compare it very carefully to what a classical mechanical description of that same system would predict, because they're very, very different. And in this class here, in this chapter, it's important for the student to learn that classical and quantum descriptions of where particles move and how they move are very, very different. So in the particle in a box type problems, we talk about probability densities. We do it quantum mechanically. We get energies and wave functions. One of the important things is we learn that these energies are discrete. That is, they can only assume certain values because the wave functions obey certain things called boundary conditions. Just like a violin string, when it's held down on the right and on the left, its wavelength can only be certain values. Half a wave fits inside the length of the left to right distance, or a full wave, or 1.5 waves, or 2 waves, and so forth. So that's what we learn in this part in here. Another thing that we do is we talk about time propagation of wave functions, because a lot of problems in chemistry don't involve just forming molecules and atoms in certain energy states, but they involve the time evolution of the wave function. So we have to learn about, at least at the elementary level in this chapter, if we have a wave function at some time t0, how does it move forward in time under the time evolution of the forces that govern the behavior of that system. Then we move on to talk about the same kind of particle in a box type problem, but in more than one dimension. That is, this would be appropriate for electrons trapped on the surface of a solid, maybe moving in the x and y direction, or within the electronic bands of a crystal moving in the x, y, and z direction if it was a metallic crystal with very loosely held electron density, so the electrons could move freely, more or less, in all three dimensions. And the treatment of higher dimensions 2 and 3 is not just the obvious extension of the treatment of one dimension, because the number of energy states per unit energy, the so-called density of states, varies very dramatically from one-dimensional to two-dimensional to three-dimensional problems. So it's important the student learn about this kind of thing. So again, in 2 and 3 dimensions, we have a Schrödinger equation, we have boundary conditions, we get out quantized energies and wave functions, and this part of the chapter deals with that situation. Then finally, just like in the Bohr atom, where the quantization of the de Broglie wavelength around the circle of the Bohr orbit is used to quantize the energy levels of the Bohr atom, and just like the quantization of the particle in a box problem, where the wavelength of the wave function from left to right, it has to fit into this box of length L, so that half a wave or a full wave or 1.5 waves fits inside the box. There's another way that you can get the energy levels and even wave functions. Instead of quantizing wavelengths, you can quantize a quantity called the action. And the importance of this is, number one, it's now a very powerfully and widely used tool in treatment of multidimensional problems, where the actual finding wave functions and wavelengths and the spatial probability densities of a problem are very difficult. But treating the so-called action, which is a classical mechanical object or quantity, is something that you can do in higher dimensions. And there nowadays are very powerful, approximate, but still fairly accurate methodologies for using classical descriptions of actions. And we'll learn in this chapter what the action is. It happens to be a certain integral involving the momentum and the displacement of the particle along that trajectory. But these actions can be used to also get energy levels and get wave functions. And then finally, at the end of this chapter, I give a summary, as I will in all the chapters.